electrons in the conduction band and the density of holes in the valence band. We have two equations, and also we have calculated the Fermi level in intrinsic semiconductor, and we have formulated, that is position of the Fermi level in intrinsic semiconductor. Okay, in previous class we have discussed about the n-type and p-type mechanisms, that is conduction. So let us have once again recollect what we have said, that is how the mechanism in n-type semiconductor. So you can look at the slide, you have two pictures, left and right side, right? So here we are speaking at T is equal to 0 Kelvin, that is at absolute zero temperature. So this is the band diagram of the n-type semiconductor, right? Now you can see here, this is the structure. So when silicon atoms doped with the phosphorus, so we can have the donor impurity contributes free electrons. Okay, so because of this free electrons, that is donor impurities. Now coming to the band diagram, so we have an energy diagram here, right? So you can see the valence band where the electrons are present here, and you have a conduction band now which is empty, right? Now you can see the here there is a labeling of the energy band diagram. So this is the energy of the conduction band, where the bottom level of the conduction band you can see here, whereas in same intrinsic semiconductor. Then below that you can have the donor energy levels. We call it as donor energy level, that is ED, where you can see the electrons, that is free electrons of donor impurity. That means phosphorus atoms you can see here. This is what free electrons you can have here. They are completely filled in this donor energy level, you can see here. So that's why we call it as free electrons of donor impurities. Okay, so how the conduction takes place in this n-type semiconductor is simply at zero at temperature greater than what happens, these electrons jumps. I'll show that one. Then coming to your valence electrons, so they are bound to the covalent bond, so there is no breakage. That means they are immobile. We can say the electrons does not move. Why? Because we are considering a T is equal to 0 Kelvin, right? Now you can see here valence band edge energy level, and this is called intrinsic Fermi level. I'll tell you why you are calling intrinsic Fermi level. Why? Because it is exactly midway between the bottom level of the conduction band and top level of the valence band. So this is called intrinsic Fermi level. Okay, now you can see the other side. So we are speak about this at T is equal to 0 Kelvin, that is its absolute temperature. Now when the temperature is greater than some other, that is T1 is greater than Tk, or at room temperature, that is 300 kelvins. So what happens here is, now you can see here slowly what happens, the electrons in the donor energy level jumps into the conduction band, leaving a positive immobile ions here. Positive, see you can see here the electrons jumps into the conduction band. See here, all electrons are excited in the conduction band from donor level, not from valence band here. Okay, now further increasing in temperature, what happens? Okay, see whatever the electrons present in the donor energy level completely jumps into the here. Now what happens? Further increasing in temperature, slowly the electrons in the conduction band start exciting from valence band to the conduction band. Okay, so keep it in mind, the conduction the current in n-type semiconductor is due to the free electrons which are in the donor energy level, not from valence band. So these are the electrons which are responsible for the conduction current in n-type semiconductor, not from the valence band here. Now over here, so when the electrons jumps from valence band to conduction band, we can say there is a vacancy created. So we can say holes create in the valence band when electron gets sufficient thermal energy and jumps into conduction band. That is due to thermal excitation. Okay, so we can call it as here you can see here, you can see positive immobile ions, isn't it? These are called donor ions. Why? Because the electron jumps, there leaves a positive immobile ions. Okay. Now coming to the structure representation of n-type semiconductor, you can see here. So these are the free electrons. You can see here. These are the free electrons, and these are the positive donor ions. Okay. Now you can see immobile donor ion of positive charge. Here, the majority carriers are nothing but electrons, and the holes becomes minority charge carriers. So this is about the N type. Okay, I think everybody understand by looking at this diagram. Okay, and coming to the P type semiconductor. So in P type semiconductor, so again we have a two diagrams. On the left side, you can have at absolute zero. Okay, so what happens here? Same. You can have the Fermi level, that is intrinsic Fermi level, but coming to you have here, you have a acceptor energy level. So we can call it is EA. EA is nothing but acceptor energy level, right? So what is happening here? It is doped with some boron atoms, right? So incomplete bond and impurities ready to accept an electron to complete the bond. So you can see there is a vacancy. Okay, to form a bond we require one more electron here, isn't it? There is a deficiency of electron here. So coming to the energy band diagram, similarly you can have here. So here all electrons, see here, there creates a vacancy. What happens here? To fulfill this vacancy, the electron comes from other, breaks the bond and comes and fill the covalent bond. So this is a cyclic process. So here also same, you can hear creation of a hole, isn't it? Again, the electron comes and fill the vacancy here. Now you can see here, these are called negative acceptor ions. We call it as negative acceptor ions, right? You can see here the same process you can have here. So these are the majority carriers are nothing but holes, and minority charge here comes nothing but electrons. So you can understand here, right? Here the electrons jumps from valence band to the acceptor level here first, isn't it? So in this previous one, you can see here these electron jumps into the conduction band, but here we can have these electrons which are present in the valence band jumps into the acceptor level. Why? Because there is a deficiency. So what happens? There creates some vacancy again, right? Again, what happens? These electron jumps into the conduction band here, and there create some acceptor ions, negative immobile acceptor ions we call it as, isn't it? So because of this, there is a conduction, isn't it? Conduction current in P-type semiconductor. That is the difference between N-type and P-type. Okay. So in N-type, we can say that the electron jumps from donor energy level to conduction band. Here, from valence band to the acceptor energy level, from acceptor to the conduction band. Okay. So this is about the mechanism in conduction mechanism in N-type and P-type semiconductors, right? Okay. Now let us have uh, the estimation carrier concentration in P-type and N-type semiconductors. Okay, so let us have that one. So okay, so let me have the previous. Let us have that one. Mm, yeah. So let me take this one. Yeah, you can have the left side LHS. You can have a some equation. So this is the belongs to the density of holes. Why? Because sorry, density of electrons in conduction band. This is the equation you got. Similarly on RHS, why? Because we use the same equation for finding the uh, carrier concentration in N-type and P-type semiconductor. So let us recollect. So what is the expression we have here? So LHS is the density of electrons in the conduction band. On RHS, you can have the density of holes in valence band. Okay, so these two, making of these two expressions you can find here, right? So let me move to the first, uh, the how to find the position of a Fermi level in eccentric semiconductor, that is impurity semiconductor. First, all of you put the heading, that is Fermi level in extrinsic semiconductor. So let me explain that, right? So first let us take the n-type semiconductor. So let me pick the diagram here, same. So you have a valence band here, right, and the conduction band here. And coming to the n-type, just now we have done the mechanism in the n-type semiconductor, that here the donor level is exactly below the conduction band here. So let me have that ED represent, that is ED. Okay, this is the donor energy levels, right? But in intrinsic semiconductor, so we have find the position of Fermi level. What is that one? It is exactly between that. Okay, so we can say it is exactly between. So you also got the expression for that one, right? Now you can find this is the uh, Fermi level. So you have formulated that is a position that is exactly halfway between the conduction band and valence band. This is the expression you got. Similarly, in intrinsic extrinsic semiconductor, so there is some, you can have the curve, isn't it, which is having the different position of the Fermi level. Okay, now this is the energy gap what you have. This is exactly off of the energy gap, isn't it? So the distance, the gap between the conduction band and valence band is nothing but energy gap. So let me pick, this is the off of the energy gap. This is off of the energy gap. Now let me, why this curve exists, because here, so in n-type semiconductor, the Fermi level lies above the middle of the energy gap, because there are more electrons in the conduction band than there are in the holes in the valence band, isn't it? Okay, so this is the why we Fermi level lies above the middle of the energy gap, and because more electrons in the conduction band than there are holes in the valence band, because of that one. Here, to find the position of the Fermi level, that is changes with impurity as well as temperature. Okay, so that's why in intrinsic semiconductor, it depends only on temperature. But coming to the n-type semiconductor, because of impurity, so we consider both parameters. One is temperature, which is varies with the temperature, and impurity, that is doping, depends upon both. Okay, more the dopant, more the conduction, more the temperature, more the conduction, isn't it? Okay, so based on these two parameters, what is happening is, let me explain that one. Here, at t is equal to 0, the donor levels are all occupied, but there are no electrons in the conduction band. Therefore, Fermi level EF lies between the donor level here. See here. So taking from this first position, so what is starting point, why I can explain is that one. Here, all the electrons are occupied here, completely filled here. Why? Because n-type semiconductor, so all donor atoms are present here. All donor electrons are present in this donor energy level, isn't it? Okay. So what, at 0 Kelvin, no electron is excited to the conduction band. So let me say that more is concentrated here. Okay. Now, if we increase the temperature, what happens? If the increase the temperature, so here we can say the Fermi level EF lies between the donor level and the bottom of the conduction band. That what we say here. This is a position starting from here. Okay. Now further increase of temperature, what happens here is slowly the electrons which are present in the donor energy level jumps into the conduction band. So what happens here? The Fermi level moves downward, slowly decreases. The curve decreases. So if the temperature is increasing, what happens? Total, that is half of the electrons from the donor energy level jumps into the conduction band. And we can say the point here dot. The dot represents is that the temperature at which, the temperature at which that half of the donor donor electrons in the donor energy level is occupied in the conduction band. That means suppose there are 100, we can say there are 50 donor electrons in the donor energy level. That means um, there are 25 are excited to the conduction band at a temperature, that means here off way we can say that one. So the same point we can have here, we can say that, okay. So what happens here, as the temperature is increasing here, further increasing in the temperature, okay. So at the temperature at which half of the donor states have become empty, and EF coincides with the donor energy level. So what happens here, here as the temperature is increasing, the energy EF will decrease here. So it reaches at a point F where that means half of the donor atoms are excited to the conduction band. So further increasing in temperature, what happens is the EF comes downwards. That means it reaches the half of the energy gap. So what is the meaning of this one is, now what happens here, when the half of the donor atoms jumps into the conduction band, if further increasing in temperature, what happens, slowly the electrons which are present in the valence band starts excited to the conduction band. Okay, so up to this point, what happen is all donor atoms are excited to the conduction band. So below this represents is the downward of Fermi level is that here slowly the electrons get excited from the valence band to the conduction band, isn't it? Now further increasing in temperature, what happens, the Fermi level slowly comes downwards, okay, and reaches the half of the energy gap. So this point represents is that one, okay. Here what happens here is the number of electrons present in the conduction band is equal to the number of, you can see here, okay. The crystal behaves like an intrinsic semiconductor when the thermal excitation of electrons in conduction band are more than electrons there, okay. So what happens is the number of electrons present here is equal to here. So when both are equal, so we can say that this n-type semiconductor behaves as an intrinsic semiconductor, okay. So why, that's why the Fermi level is decreased at this point. So at this point what happens, this total crystal, so what you have taken the crystal, that is n-type semiconductor, behaves as a intrinsic semiconductor, okay. So we are talking about only temperature, isn't it? So here as the temperature is increasing, what happens, the Fermi level slowly comes downwards and becomes intrinsic semiconductor, isn't it? So that is the most important here, that the crystal behaves as an intrinsic semiconductor when the thermal excitation of electrons in the conduction band are more than electrons there, isn't it? So this is about the intrinsic semiconductor, sorry, n-type semiconductor, that is Fermi level position. So similarly, you can find for the n-type semiconductor. So let me have that one, same process, okay. Now you can see the picture here. So here we can see the acceptor energy level. Okay, here the Fermi level goes here like this, isn't it? Now here also at this point, this n-type p-type semiconductor behaves as an intrinsic semiconductor, isn't it? Just now we have in the n-type semiconductor. So this point, at this point, what happens here is the p-type semiconductor behaves as a intrinsic semiconductor. So what happens here is, here at 0 Kelvin, what happens, okay. So here all the electrons which are present goes to the acceptor level, isn't it? Further increasing, what happens here, half of the acceptor atoms goes to the conduction band here, right? So here it beats the point, and further increasing, what happens here, it goes in downward directions and it becomes the intrinsic semiconductor. Same what we have done in the here also, same. This will be in reverse condition. This will be here, right? So in p-type semiconductor also you can have this type of layer, okay. So here I mean to say that just we uh, uh, have learned what is the position of a Fermi level in n-type and p-type semiconductor. Similarly, you can find the equations for that one, just like you have find the in case of intrinsic semiconductor, that is EF is equal to EC plus EV by 2. Similarly, in n-type and p-type, we can formulate the exact formula for the Fermi level. So in coming estimation of charge carriers, we can find that one. Okay. First, let us find the estimation of carrier concentration in an extrinsic semiconductor. So let me explain that one, right? Now you can see the put the heading same. We are having the estimation of carrier concentration in extrinsic semiconductors. Okay. In the first case, let us have the concentration of electrons in the conduction band of a n-type semiconductor. Okay. Similarly, you can find the concentration of holes in the valence band of a p-type semiconductor. Why? Because in n-type semiconductor, majority carriers are electrons. In p-type semiconductor, the majority carriers are nothing but holes. Okay. Now let us find the carrier concentration of electrons in conduction band of an p-type, n-type semiconductor. For that, I have taken the chosen the diagram here. Okay, same diagram. So just for understanding purpose, so you have a energy donor energy level where the electrons are occupied completely at 0 Kelvin. If further increasing, what happens? Slowly, these electrons goes to the conduction band and they create some positive immobile donor ions, isn't it? Now let me have, already we have solved that one is ed, let e suffix d is the energy of the donor level, right? Then nd represents donates the number of donor atoms per unit volume. Here the number of donor, how many donor atoms are present for a given volume, just we are assuming that is nd denotes, isn't it? Now here one important point is there is the concentration of electrons in the conduction band must be equal to the number of vacancies per unit volume in the donor level. Here is, isn't it? Suppose this electron is jumps into the conduction band, they create some vacancy here. Okay, that must be equal. We are saying that here the concentration of electrons in the conduction band must be equal to the number of vacancies per unit volume in the donor level. Okay, if you know this condition, we can have that one. Now here some note is there, very important is that one, since the donor level is very near. Why? Because this is very near to the conduction band, here the effect of valence band can be neglected. So making use of this condition, you can formulate the concentration of electrons in n-type semiconductor. So let me have the same expression what you have here, right? So here the density of electrons per unit volume in the conduction band. So how you got this equation? In intrinsic semiconductor, you have that one. That is, we are finding the density of electrons in the conduction band. So you have an equation. Just now, in the starting of my lecture, I have just recollect the LHS and RHS, isn't it? So same expression I have used here. That means you are finding the density of electrons in the conduction band. So what you have, any same expression, same notation we use here. So you got the equation 1. Same expression we are finding here. Here we know that EF is nothing but energy of the Fermi level, and where EC is nothing but energy corresponding to the bottom of the conduction band. So the energy of the bottom of the conduction band. Now here, now let us find the density of empty donors, that are the number of vacancies per unit volume in the donor level. So just now you have now, this is the condition. Okay. So now you got here the concentration of electrons you got. This is a equation you got. Similarly, you are finding the number of vacancies per unit volume in the donor level. This you have to find now. For that, we have equation here, isn't it? The density of empty donors or number of vacancies per unit volume in the donor level is given as nd into 1 minus f of e, isn't it? This is the formula we have here. Okay, so what is f of e? So what is f of e? That is Fermi distribution function you have done in intrinsic semiconductor. That is f of e, isn't it? So what is f of e here? Just you uh, um, rewrite here. So that becomes 1 by e to the power of ed minus ef by kt plus 1. This is the Fermi distribution function in case of n-type semiconductor. So what is the difference here? You're writing ed instead of ec, you're writing ed. Okay, now let us simplify this one. You got that is equal to nd into e to the power of ed minus ef by kt by 1 plus e to the power of ed minus ef into kt. Okay, now finally what you got expression here is density of empty donors is equal to nd into e to the power of ed minus by kt. So how you got this expression? So what about the denominator? You're writing only numerator. So what is about the denominator? You can see the condition here. Okay, okay, you can write here. So we can say that ef minus ed is very much greater than kt. Okay, now how can you write ed minus ef is very much less than kt? So that implies you bring kt to the denominator, which is less than 1, or when you apply the exponential here, e to the power of ed minus ef by kt is very much less than 1. So here the denominator is approximately equals to 1. That's why I have put it equation 2 here. That means the density of empty donors is equal to nd into e to the power of ed minus. Why? Because the denominator is approximately equal to 1. So this is the equation what I got. So I got the both the equations, that is density of electrons in the conduction band and density of empty donors. Both equations I got. So making of equation 192 as per this condition, that means we have to equate. You have to equate equation 192. Okay. So you got here equating equation 1 and 2. So we can have, so equate the both the equations, what you got here. So taking log on both sides, taking the log, apply the log on both sides, isn't it? So what you got, log 2 into 2 pi m e kt by h square. So there is some missing, it is 3 by 2. So all of you, there is some mistake here. 3 by 2 plus ef minus ec by kt is equal to log nd in plus ed minus ef by kt. You got these equations. So rearrange these equations as per our requirement. So I got ef minus ec minus ed plus ef by kt is equal to the remaining terms what you have here, right? So let me take ef outside. So I need Fermi level. So 2 times ef is equal to ed, okay, plus ec plus kt log into, you got these expressions. So finally I'm going to find the energy of the Fermi level, that is ef. So finally I got ed plus ec by 2 plus kt by 2 into log of nd by 2 times of 2 pi m e kt by h square by 3 by 2. This is the equation I got. Okay, now so let me apply this ef, the value I got the value of ef. Let me substitute this ef in equation 1. Okay, so what is the equation 1 you got here? In equation 1, this one. Okay, so I want to substitute the value of ef in equation 1, isn't it? Okay, these all mathematical expressions to solve that one. So I want to substitute here ef value, okay, in equation 1. So I got here, see here, same expression, that is density of holes here. So just I apply e to the power of this all term into ef, isn't it? So I got this equation here, right? So on simplification, on simplifying, right? So this is the equation I got here. So okay, right? Now let us take assign some symbol here. So what is that is here, uh, ED minus EC is equal to delta minus delta E, isn't it? Just for understanding purpose. Okay. Now finally, what you got, because 1 by 2 is a common, so I have taken 2 into n into 1 by 2. So I got these equations. Then e to the power of minus delta E. Okay. What is this delta E? It is nothing but ionization energy of donor. Okay, that is I can write delta E is equal to EC minus ED, which is the ionization energy of the donor. Okay, so what happened here, if you put T is equal to 0 in equation 3, so I can find the formula for Fermi level. That means here, why? Because at T is equal to 0, I can find the position of the Fermi level. You put T is equal to 0, so what happens here? Finally, you got here that is EF is equal to ED plus EC by 2. So this is the position of the Fermi level which lies exactly halfway between the donor levels and the bottom of the conduction band, right? So we have the condition for that one. Let me have. So just now we have find now. So what is that? Yeah. Now you can see here. Okay. So this is the position, starting position of the uh, Fermi level here. Fermi level position. That means it exactly halfway between the donor and the conduction band level. Okay, that's we are going to have mathematical expression for that one. Okay, so this gives that, right. So EF is equal to ED plus EC by 2. So similarly, we have a expression for intrinsic semiconductor also. You have to keep it in mind, all of you, right? Now, next, let us have the same expression. This is very simple as compared to intrinsic semiconductor. Okay, so this is very simple. Okay, we have only almost 3 equations. That's all. Just we have to understand this principle. If you understand this principle, you can frame the formulas and you can substitute in that one. Okay, so this is a final what you got the expression here, right? Okay. Similarly, we can find uh, so this is another one where it depends upon here. So from equation 4, it is clear that the density of electrons in the conduction band is directly proportional to square root of the donor concentration. That we have that one. Okay. Now, if you take the graph that is between the log Ne and 1 by T, for any impurity semiconductor containing different donor impurities. So we can have here, so ND1 is very much less than, that is, this has greater impurity, isn't it? So these are the densities of the impurity atoms. Okay, we can find here. So there is some condition is that in that intrinsic semiconductor. So this is not much important, just for understanding we can have that. So let me have the second one next. Concentration of holes in the valence band of a p-type semiconductor, right? Okay. Now let us find the concentration. Similarly, you have find the concentration of electrons. Similarly, the concentration of holes in the valence band of a p-type semiconductor. So you can see here, this is a diagram where you can have the acceptor levels. Okay. So what happens here? The electrons comes here, right? And these are goes to the conduction band here. Now let me have the notation here. So here EA is equal to energy of the acceptor level. So same ND is donates the number of acceptor atoms per unit volume. The same condition here. Okay. So the same condition, what is the condition you have here? Isn't it? The concentration of holes in the valence band must be equal to the number of vacancies per unit volume in the acceptor level. That is the same principle we apply for here also, right? So what is that here, right? Now, same expression you got. What is the density of holes in the valence band as per the intrinsic semiconductor we have? It is same. NH is equal to 2 times 2 pi m h kt by h square to the power of 3 by 2. So there is some missing always. E to the power of EV minus EF by KT. That is equation 1. Okay. So here name next the number of electrons per unit volume in the acceptor level. So which is called Na into F of E. Just now we have denoted Nd into 1 minus Fe. Here Nd into Fe. That's all. Simple. Why? Because this expression we use in intrinsic semiconductor. That is, you are finding the concentration of electrons in the conduction band, isn't it? The same expression is applied to here in p-type semiconductor. So we can say the number of electrons per unit volume in the acceptor level. So this is an expression. Now you know the value of f of e. Simple. E to the power of 1 by e to the power of a minus ef into kt plus 1. Simple, very one. And using the same condition here, okay, since ea minus ef is very much greater than kt, so bring the kt into denominator, which is greater than 1. Okay, so finally you got 1 plus e to the power of a minus ef into kt very much equal to e to the power of ea minus ef by kt. Okay, so that's why the expression becomes here the number of electrons per unit volume in the acceptor level, isn't it, is equal to Na into, write this expression. You make it equation 2. Now, according to condition is that you have to equate the equations 1 and 2, isn't it? Same. At equilibrium, what we have? Okay. So at equilibrium, equating equation 1 and 2. So just you have LHS and RHS. So taking same log on both sides, right? Taking log on both sides. Okay. Now you can have this one, the same expression. You are going to find EF. Similar, same. I want the value of EF, isn't it? So here, the next. Now, I got the value of EF here. See here, I got the equation 4. Now, putting this equation 4 in equation 1, same. Just like in N-type semiconductor, you substitute the value of EF in equation here. Same. You find the value of EF here. You're substituting the value of EF in equation 1, right? So you got here, same. You got here the equation 5 here. Okay, similarly. Now putting same, instead of Ea minus Ev is equal to delta E. So this is the ionization energy of the acceptor atoms. Acceptor atoms. So finally you got minus delta E by kT. Now if you put T is equal to 0, isn't it? In equation 4, what happens? Where is the equation 4? Here. Yeah, you put T is equal to 0 here. So it becomes EF is equal to EA plus EY by 2. So what you understand from here, we can say that, okay, the Fermi level is exactly halfway between the acceptor level and the top level of the valence band, right? Isn't it? So you got the Fermi level in N-type semiconductor and P-type semiconductor. Okay. So by making the estimation of carrier concentration in eccentric semiconductor, we also find what is the position and what is the formula for Fermi level. Okay. So these are about the uh, estimation carrier concentration in N-type and P-type semiconductor, right? Okay, you make use of this one because they may ask in the examinations that to solve the Fermi level position in n-type, p-type and intrinsic semiconductor. Okay, simply you're substituting the values, you can get the position of that one. Okay, so this is about the estimation carrier concentration in eccentric semiconductor. We have find the Fermi level positions also. by making of equations of intrinsic semiconductor. Okay, so anything else you have? Yeah, any questions? Yeah, no questions, please. Okay, you are very eagerly waiting for the attendance. I understand that. No problem. So tomorrow we discuss about the Hall effect. Okay, making use of this carrier concentration, we have a good experiment, isn't it? What is Hall effect? In the same way, let us find some how the Fermi level depends upon the temperature and doping. So this is very important. Same, we pick some main points from this intrinsic and eccentric semiconductor. We put together and we show how this Fermi level depends upon temperature as well as doping. Okay, this is most important, right? And we also have the what is the importance of Fermi Dirac distribution. I'll show what does also, and along with the Hall effect. Hall effect is the most important, and what are the applications of Hall effect we discuss in tomorrow class, right? And for I section students, tomorrow we have at 9:40 both I and J. Once again, I repeat, tomorrow you have a class at 9:40 to 10:40 instead of 10:40 to 11:40 for I section. Okay, so there is a life skills class now. So I think I will take the first hour for the I section, and for J section you have as usual the first hour. So both the sections tomorrow at 9:40 to 10:40, right? So let me take the